Hello everyone, my name is Changbo. I'm very excited to present our paper towards extracting highlights from recorded live videos, an implicit crowdsourcing approach. This is joint work with Ruochen Jiang, my supervisor Dr. Jianan Wang, and Dr. Chi Wang from Microsoft, and Dr. Yudian Zheng from Twitter. Let me start my presentation with a few questions. Have you ever watched the live streaming videos over Twitch or the other platforms listed below? I believe your answer must be yes, especially in the current coronavirus situation. For example, I have been following up with Canada daily briefings to get the most up-to-date information about the coronavirus and the government decision recently. And let me continue to ask you another question. What if you missed the live streaming, or you are just super busy and are only available to watch a long recorded live video in a very short period of time? Maybe what you are going to do is to randomly drag the progressive bar and have a quick scan of the whole video. However, this is not good, since first, you may miss many interesting highlights, and second, you may waste your time on many uninteresting video clips. If you are facing this problem, you will find the answer from my presentation. Our method could automatically extract top K highlights from a long recorded live video. The K is specified by the user. Here, we show an example from our experiment. From a 2-hour .2 video, we extracted a 2-minute video of 5 highlights. Before we go into the details of our workflow, I will introduce a little bit about the existing works and clarify why our workflow is different from these existing methods. Detecting highlights is not a new topic. Some methods are proposed to detect highlights from baseball or soccer games. However, there are domain-specific solutions, which means we need to design different algorithms for different domains. Another branch of research is deep learning-based methods. This usually require large training dataset and high computational cost. These are still not very general methods, because for different domains, people still need to collect domain-specific data to retrain the models. For example, as far as I know, it's safe to say in all cases, if we have a CNN model trained by NBA data, we cannot apply it on .2 data to predict highlights. The main reason why all these methods are not general is that they only access raw video data to either train the model or extract features. So the question is that, besides the video itself, is there any other resource we can use to detect highlights for more general types of videos? We would like to introduce implicit crowdsourcing to tackle the highlight extraction problem. The idea of implicit crowdsourcing is to leverage humans' ability to solve hard computational problems in an unobtrusive way. For example, reCAPTCHA leverages users' login operations to help digitize notebooks. Web search engines use users' click-through data to optimize search ranking. These implicit feedback are very effective. For recorded live videos, we consider 2 types of implicit feedbacks. The first one is viewers' chat messages, which are generated in the video's live streaming session. The high-level idea of using messages is that when viewers are sending a lot of chat messages on some point of the video, in some sense, it's like to vote for the video content. If thousands of viewers are chatting on the same point of the video, probably this point has some very interesting content. The second implicit feedback is the viewer's playing record, like which part of the video has been watched by each viewer. Intuitively, if different viewers repeatedly play the same part of the video, probably it contains a highlight. These are the implicit crowdsource information we want to leverage. By avoiding touching video content directly, our methods have good generalizability on different types of videos. So let's talk about our highlight detector called Lightor. Based on live streaming videos chat messages, we have the highlight initializer, which outputs the approximate starting point of the highlight without the red dots shown in the middle picture. Based on this, we build a second component called highlight extractor. With the help of the red dots, highlight extractor keeps collecting viewers' playing records to refine the boundary of the highlights. And finally, we extract accurate highlights. For the highlight initializer, the input is the user's chat messages. The output is an approximate starting point of the highlights. The naive thought is that when a highlight happens, there are going to be a lot of chat messages. Maybe we can simply use the peak of the number of chat messages at the starting point, like the red star here. But the naive implementation have two problems. The first one is that chat messages are very noisy. In a short period of time, there might be repeating advertisement, random messages, or debating messages between viewers. These noisy cases will also produce a peak as well, the same as the highlights. The second problem is that there's a natural delay between the highlights and its comments, because people can only comment on a highlight after they have seen it. For example, here, the red star in the figure here represents a peak of the viewer's comments. Well, in fact, the true highlight start is a green line here. We can see that there is a 20 seconds delay here. To address the noise chats and the delayed comments problem respectively, we designed two stages, prediction and adjustment. In the prediction stage, the goal is to determine whether the messages within a time window are talking about highlight. If a highlight is detected, we will then assign it a starting time in the adjustment step. To address the noisy message problem, we designed three robust messages features in this prediction step. Besides simply use the number of chat messages, we also consider the average length of the messages and their similarity. Because we observe that when a highlight appears, people will tend to send short and similar messages. Using these three features, we can train a binary classifier to predict whether the window of messages corresponds to a highlight. Next step in the highlight initializer is the adjustment step. We use it to address the delay between common peaks and the start of the highlight. We currently consider this delay as some linear variable. We trained a very simple model to calculate it for now. It could be further explored in the future work. In the earlier example, the best delay is 20 seconds. By subtracting the delay from the peak, we can get the approximate start of highlights. Which are the red dots here? Highlight extractor will take these red dots as input. Another source of input is users' playing records. These playing records are like viewers' votes, saying that, okay, this part of video are kind of watchable. Finally, highlight extractor will output refined highlight boundaries based on these inputs. We will use an example to illustrate how this highlight extractor works. When a viewer clicks on the red dot, she will face two cases, that the red dot is before the end of the highlight or is after the highlight. Let me explain it in more detail with this soccer video. Let's first consider the first case. After clicking the red dots, viewers see Real Madrid scored, which is definitely a highlight. In this case, viewers will probably just keep watching the video. Imagine different viewers are doing the same thing. Their playing records will tend to center together. By aggregating these centered playing records, we will have a better highlight boundary estimation. In the experiment, we use medians of playing records start and endpoint as a boundary of a highlight. We do this intuitively to further refine the boundaries until the boundaries are stable. In the second case, our indicator is after the highlight, so the viewers will miss the highlight. What will they do in this case? They will tend to seek backward or skip to search for other highlights. So their playing records will be more random in this case. It means our indicators are not good enough. Then we should refine it. But how? We just move the readouts backward a little bit, try to change this case into the first case. Like the readout is before the highlight. By intuitively collecting these playing records, classifying the two cases of readouts and adjusting them, we can eventually get the accurate boundary of the highlight. Let's have a look at our experiment. We have two datasets, Dota2 dataset and the League of Legends dataset. Users' interaction data are collected through Amazon Turk by a simulated task. We use video precision at K to evaluate the precision of the start or endpoints of the extracted highlights, where K is the number of highlights that users specified. We use chat LSTM as our baseline. It's the state-of-the-art deep learning-based method to detect highlights over chat messages. In terms of training datasets, the figure here shows the precision of our method and chat LSTM. We first train both our method and chat LSTM on one video and test it on 50 videos. We can see that in the red bar, our methods outperforms chat LSTM by over 20%. Then we increase the chat LSTM's training data to over 100 label data. The blue bar is the testing result. Although its performance increased a lot, it still performed worse than our methods, which means in terms of training data, our methods require far less training data than deep learning methods here. To compare the generalizability of the two models, we train both models on IOL data and test them on both Dota2 data and IOL data. As you can see from the figure, our methods perform similar on both datasets. For chat LSTM, there is a gap between two testing datasets. We can see that our methods have a better generalizability comparing to this deep learning method. We have extensive experiments in our technical report. Please refer to our demo page later if you're interested. So here are some takeaways. We propose an implicit crowdsourcing workflow, Lightor, for highlight extracting from live streaming videos. Comparing with deep learning, it requires lower training cost with higher generalization and precision. We do not argue to totally replace deep learning on highlight extraction. Instead, we provide an alternative promising method in the favor of implicit crowdsourcing to do highlight extraction. Thanks for watching the video. Please see our demo through the link below or scan the QR code. Thank you very much.